Hello and welcome back to QED and QCD. In the last lecture we calculated our first scattering amplitude for a process. Now of course what's measured experimentally is not directly the amplitude square but the cross section. The difference is a flux factor and a phase-space integral. So today we will be looking at how cross sections are calculated by phase-space integrals. We won't actually be doing much of phase-space integrals, but we will look at how they're parameterized. Nowadays, of course, many phase-space integrals are done by Monte Carlo methods on a computer because that allows one to calculate simultaneously the distributions in many observables, apply cuts, etc., which are all difficult if one needs to do the phase-space integrals analytically. However, sometimes it is convenient to be able to do the phase-space integrals, or at least some of them, analytically, because then one can study, for example, the cross-section as a function of a single angle. And that's what we'll do. So, phase-space integrals. And cross-sections. So, in principle, we must integrate the the momentum of all the particles over the final state that is accepted in the detector. Now, that phase-space integral is a four-dimensional integral over the energy, the px, py, and pz, but with the constraint that the on-chill condition for each particle, that the momentum squared of the particle is equal to its rest mass squared is met. So if we look at the phase-space integral over the final state particles, then there's a product, one phase-space integral for each particle of a four-dimensional integral pf normalized by 2 pi, and then so there's one such factor for each f, and then there's an overall in that factor there's also the condition that the energy momentum on-chill condition is fulfilled, that pf squared minus m squared is fulfilled, but also we want to integrate, here there's a four-dimensional integral including the energy, and we want only positive energy solutions. So there's a step function saying that pf0 must be positive. So in principle, what we have is a product over f of the four-dimensional, the energy integral here, so the integral over d pf0, of course, can be done using this delta functional, right? So we have a four-dimensional integral with a scalar condition here. So we know that that should reduce to a three-dimensional integral. The delta functional exactly allows us to perform one of the integrations, and we choose that to be the energy integration here. So that each of these integrals instead becomes a three-dimensional over the px, py, pz. Now what's left, you see here, is then that the 2 pi 4, one of the 2 pi factors is cancelled with that 2 pi, so we get a 2 pi to the power 3. Now the integral over the what we have here is 1 dpf0. What we have in here is a condition on pf0 squared. So the Jacobian will be a 1 over 2e Pf0. So what we get here is from that, using the delta functional to perform the Pf0 integral, we get another factor 2EF. And that's the integral we need, or that's the phase-space integral we need to integrate over, whereas now the EF is on shell. Now, this final expression separates the dependence on E and P, but it is still Lorentz invariant. This one here is a Lorentz invariant integral. Lorentz invariant measure for the phase-space integral. The scattering matrix element is Lorentz invariant. So when we integrate it with a Lorentz invariant measure, we still get something that's Lorentz invariant. This here is written in a way that doesn't look invariant because it separates out the px, py, pz and the energy, but actually it is. It's exactly equal to the first line here. And the factors of 2 pi just correspond to the conventions. Now, when we want to express the cross-section, then we need to normalize with the flux of the incoming particles. The flux factor can be written as F is equal to 1 over 4 the energy A, the energy B for a scattering PA, PB going to something. The flux factor for the incoming particles is EA, EB, VA minus VB, length of that vector underneath. Let's do that. Good. Now, this can also be expressed in terms of explicitly Lorentz invariant quantities, such as 1 over square root 4 PA dot PB squared minus MA squared MB squared. Here, this is Lorentz invariant, and these are of course the Lorentz scalars, so invariant. So it's clear that the flux factor here is Lorentz invariant. Now, in the massless limit, when MA and MB goes to 0, PA dot PB is just the invariant mass. So this goes to 1 over 2S in the massless limit. Good. Now, of course, PA and PB, what I've written up here is just the integral over final state particles. Of course, due to momentum conservation, every single vertex in the Lagrangian conserves energy and momentum. So therefore, if you plug several vertices together in a cross-section or in a scattering amplitude, you still have energy and momentum conservation. It's conserved at every single vertex when the final rules are used in momentum representation. Now, that means, of course, that PA and PB are determined from the final state particles. For a given set of final state particles, there's one unique PA and PB. So that means that our sigma, our cross-section, how often do we find a given particle scattering event, will be our flux factor, how much incoming particles do we have, times our phase-space integral times our scattering amplitude, and often it's the spin summed and average, not always, but often it's a spin summed and average cross-section we are interested in, times 2 pi 4, and then the constraint that the sum over final state energies or momentum is equal to the incoming energy. Let's call that A and B. Now, this is for a scattering process. We see here that's where the matrix element enters that we calculated last time. We then have to do a phase space integral. Nowadays that's often done on a computer with the constraint that the incoming momentum is fixed by the outgoing momentum. Now, of course, if you then wanted to know not just the total cross-section, but the dependence on the, let's say, PT of the hardest particle, then you would, for the chosen phase space point on the computer, you would calculate the PT of the hardest jet and enter this contribution to the cross-section into the given bin in PT1, for example. The clever thing about doing this on a computer is then that you can calculate all the distributions in one go, in one phase space integral. Now, that's how to get cross-sections. Now, sometimes the matrix elements are also used in order to calculate decay widths. Now, for decay width, the flux factor is equal to 1 over twice the mass of the decaying particle, and therefore the decay width is 1 over 2m. That was the flux factor, and then the same product over final state particles, d3pf 2 pi cubed 2ef, our, let's say, spin summed average matrix element, and the condition that the sum over final state momenta is equal to the momentum of the decaying particle. We can now return to Coulomb scattering to calculate the cross-section as a function of the scattering angle. So let's write down here, return to Coulomb scattering, which was the E mu to E mu. Now what we have there is that the cross-section would be equal to the flux factor times the phase space integrals of the final state particles, which we called, let's say, P prime, K prime, PK. So we would have here D3 P prime 2 pi cubed over 2E prime, and a d3k prime over 2 pi cubed to okay, I'll call this E prime as P and E prime K. Should really be P prime and K prime, I guess, times the Lorentz invariant square of the scattering amplitude summed and averaged over spin, and then the momentum conserving, energy momentum conserving delta functional 2 pi cubed, saying that the components of the incoming form momenta needs to be equal to the sum of the outgoing form momenta. So P prime plus K prime minus P minus K delta functional. Now this expression is Lorentz invariant. Now that means, you know, the momentum measures here are Lorentz invariant, the scattering amplitude is Lorentz invariant, the flux factor is Lorentz invariant, and this is just a requirement that this energy and momentum is conserved, which is of course Lorentz invariant. So we can choose which frame we want to evaluate this in, and the result will be valid in any frame. So let's choose an easy frame, which is center of mass frame, where the incoming momentum of the electron is equal to minus the incoming momentum of the muon. Good. So we can easily perform the K prime integral here, for example, by using then 3 of the delta functionals, right? We have a 3-dimensional integral to perform here, and we have 4 scalar delta functionals at our disposal, so we can use 3 of them to perform that integral. So that means that we are then left with an integral saying the cross-section is equal to the flux factor. The integral that's left is the P prime integral, 2 pi cubed to E P. We have another 1 over 2 E K factor, E prime K factor. Our 2 pi cubed was used up with a 2 pi cubed here. So what we're left with then is a 2 pi and then a constraint on the energies, EP prime plus E K prime minus EP minus EK. Now, let's say that we want to express the answer in terms of the scattering angles, right? Understanding that in the Coulomb scattering, really, it's only the angles that are relevant. Since the momenta are conserved, the masses are unchanged, the angle is the only degree of freedom, the 2 scattering angles. So let's express the answer in terms of scattering angles. That means that we want to transform the integral here to with polar coordinates. So we write the 3-dimensional momentum in terms of the integrals length, the P prime, and then d theta d phi, the cos theta d phi. We just write as the omega, where the phase or the angular integral is sine theta d phi. Good. So the cross section is then the flux factor divided by, let's take out the 2 pi's here, 2 pi squared. There's a 2 pi used with the 2 pi here, so then it becomes the integral of the omega, and then a length of the outgoing momentum, P prime squared over 4 EP prime EK prime, scattering amplitude squared, and the energy conserving delta functional. Now, let's say that instead, let's say that instead of integrating over the length of the momentum, we want to integrate over the center of mass energy, or we want to express the answer in terms of the center of mass energy. The answer expressed in terms of square root s, which in the frame we've chosen is of course equal to EP plus EK, or EP prime plus EK prime. I've written the primes differently there, but it's the energy of the outgoing momentum. Now, of course, the energy conserving delta functional here ensures that the energy of the outgoing states is equal to the energy of the incoming states. Now, if we want to perform a change of variables that sends the length of P prime, exchange that variable with E, which is EP prime plus EK prime. I like the primes here instead. Then we need to calculate the Jacobian. Now the Jacobian for that energy transformation, remembering that if we change P prime, then necessarily K prime is also changed, is the E d P prime is equal to E P prime over E P prime. Like so. And that's convenient because then that Jacobian removes exactly the dependence here on EP prime and EK prime, such that the cross section becomes the flux factor divided by 2 pi squared d sigma d E, and then there should have been a dp dE, which gets rid of the EP prime and EK prime. Then we get a P prime length over 4E, the matrix element squared, and then the constraint that the energy that we had here, EP prime plus EK prime, is equal to the center of mass energy, which is the flux factor over 2 pi squared, the angular integral, and then we just write, E as square root s. So we've got a P divided by 4 square root s, and the spin summed average matrix element. Understanding here, of course, that the incoming states are determined by the outgoing states by energy and momentum conservation. Good. Now the only undefined variables here are the angles. But actually that's often measured, and what's interesting is to measure the cross-section as a function of the angle. So if one was indeed interested in the sigma d omega, then of course this angular integral is undone. And then one would get the flux factor divided by 16 pi squared, that's the 2, 4, 16 pi squared, the P prime square root s, and the square of the matrix element. So actually here one would measure more or less the square of the scattering amplitude. Directly by measuring the scattering angle dependence of the cross section. Now, in the high energy limit, where S is much bigger than the masses involved, then the Mandelstam variables become S. The center of mass energy is 4 p squared T. Sorry, we all know S is PA plus PB, the incoming, 4 momentum squared. T is PA minus one of the outgoing ones, but that's minus 4 p squared sine squared theta halves, and U is equal to minus 4 p squared cos squared theta halves. And using those, we can express the spin averaged matrix element squared as twice the charge squared, twice the charge squared, S squared plus U squared over T squared. That's a spin summed and average scattering amplitude. And if we plug in our results for S, T and U, then this becomes 2E4 sine to the 4 of theta halves and 1 plus cos to the 4 of theta halves. Now this amplitude, the square of the amplitude, has no dependence on the azimuthal angle, unsurprisingly. And using the conventional notation then, that alpha squared is E squared divided by 4 pi, then one obtains the cross section, or the differential cross section with respect to the angle, is equal to alpha squared over 2S 1 plus cos 4 theta halves sine 4 theta halves. So that's the cross section, differential cross section for our E mu scattering, for the Coulomb scattering. And that's of course something that could be measured directly and compared with this Born level prediction. So we've looked so far at the scattering of electrons of muons. Now we'll use that amplitude to calculate E plus and minus annihilation, or the cross section for E plus and minus annihilation. It may seem strange that one can use the scattering amplitude for E mu scattering to calculate the cross section for E plus and minus to mu plus mu minus. But that's due to a property of the scattering amplitudes called crossing. Let's look at that. First, E plus E minus annihilation. So what we're looking at here is E plus of a momentum P prime and E minus of a momentum P, creating a mu plus of momentum K and a mu minus of momentum K prime. Now it turns out that a property of all scattering amplitudes is that if we have a E minus mu minus of P, mu minus of K going into an E minus of P prime and a mu minus of K, like we had before, K prime like we had before, then the scattering amplitude, if one wants to calculate instead, say a mu plus, let's cross both of them, where we've got an E minus coming in, and we take this E minus and move it to the incoming state such that it becomes an E plus. minus P1, and we take the mu minus here onto the other side, such that it becomes a mu plus of minus K, and we still have the mu minus of K prime. Then those amplitudes are related by crossing symmetry. Now normally there will be some signs that would enter, so plus minus signs that would enter when that crossing is performed, but of course if one is interested in the matrix element squared, then those signs do not matter. The matrix element squared is always a positive number. Now, therefore, we can explicitly use the cross-section we've already found. We just need to remember that the momenta here is with the other sign. Anyway, so we find E plus E minus. If we take the approximation, where we ignore the electron mass, then we find that using the form of the amplitude we had before, that the matrix element squared is equal to 8e to the 4 s squared p dot k squared plus p dot k prime squared plus mu squared k prime squared. Good. Now, sometimes when one does this crossing, we can't just take over the form of the amplitude squared, because the averaging and the summing of the spins will be different. If, for example, we take a photon from the or a gluon, better, from the final to the initial state, then one had to be careful over by the summing and averaging over colors, for example. But here, since the muon and the electron have the same number of spin states, that's simple. So if we choose to work in the center of mass frame, then we get again that d sigma d omega for E plus E minus going to mu plus mu minus is equal to alpha squared over 4s square root of 1 minus 4m mu squared over s, and then a 1 plus 4m mu squared over s plus 1 minus 4m mu squared over s cos squared theta. Now let's just work in the limit again, where the energy is much bigger than m mu squared. Then we would find that the differential cross-section is alpha squared over 4s, and just have the 1 plus cos squared theta. Now, if we wanted the total cross-section, we can then find this by actually performing the phase-space integral. Now, the phase-space integral that's left is just the angular integral. And we remember that d theta is equal to sine theta d theta d phi, where theta runs between 0 and pi, and phi is in 0 to pi. phi is the azimuth, and theta here is the polar angle. Good. So that, of course, here is equal to minus the cos theta d phi. So if we want to, when we want to integrate the sigma d omega, then the only dependence we get on angle is through the cos squared theta. Sorry, yeah, so that's the one that we need to integrate. Now, that should be integrated over theta running from 0 to pi. So let's just do that. Instead of writing it as cos squared the theta between 0 and pi, we perform this change to minus the cos theta. So we have a minus 1 plus cos squared theta d cos theta, and that should run between when theta is 0, cos theta is 1, when theta is pi, cos theta is minus 1. Now, this we can write theta as minus the integral from 1 to minus 1 of 1 plus x squared dx. But of course that we just reverse the order for the integral as the integral from minus 1 to 1 of 1 plus x squared dx, which is equal to the integral of 1 from minus 1 to 1 is 2, and the integral of x squared from minus 1 to 1 is the integral x cubed from minus 1 to 1, which gives 2/3. So it's 2 plus 2/3, which is equal to 8/3. And then the phi integration here will give us a 2 pi. So all in all, our cross section for E plus E minus going to mu plus mu minus is equal to, so we had the 8/3, we had the 2 pi, and then we had the cross section, which was alphas, or the flux factors and matrix element squared, alpha squared over 4s, and then the integral of the 1 plus cos squared theta that we did. So what we have here is a 8 divided by 4 is 2, and there's an extra 2 pi that gives us 4 pi divided by 3, and then an alpha squared over s. That's really nice. We now have the total cross section for E plus E minus to muon creation expressed as a function just of the center of mass energy. Now, muons is not the only thing that can be produced from E plus E minus. Now here, of course, we can write this as it's one fermion line, so you would write that as a E minus still here, but the fermion momentum or the fermion number flow is opposite to the momentum flow of the E plus. So what we have here was mu minus, write that here, so E plus E minus annihilating to a photon, creating a mu plus mu minus pair. Now, mu plus mu minus is not the only thing that can be created. You could create quarks as well. For example, an up quark. Now, they would be seen in your detector as hadrons. Now, of course, the calculation here would be exactly the same. The spinor strings are all the same, whether it's muons or it's quarks. The difference is that you would have a different charge because the U is charged with 2/3 instead of a full electron charge. And there's another difference. You can't just create one set of up quarks. You have 3 QCD colors, 3 different types of quarks, up type, that you can create a red, a green and a blue. So therefore, the cross section for E plus, E minus to hadrons will be equal to the same 4 pi alpha squared over 3s. Then the number of colors that you have in QCD, and then also the sum from I equals to 1 to the number of flavors that you can create, and then the square of the charge of that type of quarks. So for example, 2/3 for up and 1/3 for down type. Now this is of course all done at tree level, and there will be higher order corrections. But this means that the ratio R of the cross section of E plus E minus to hadrons divided by E plus E minus to mu plus will be equal to NC and then the sum over quark charges. And that of course gives you a direct measurement of the number of colors in QCD.